This is Physics 1020 and 1090. The lecture is for Monday, April 13th. We're in Chapter 29 on nuclear physics. Here in this first video, we're going to talk about nuclear reactions. Here's our first nuclear reaction we're going to look at. We take an alpha particle and we bombard nitrogen-14 with the alpha. And what do we get out? Well, we get oxygen-17 plus something else. What is the something else? What I want you to do is stop the video, figure out what that something else is, and then come back. What you should have found is that something else is hydrogen 1. So you have 2 protons plus 7 protons, so 9 protons on this side. You have to have 9 protons on this side. This is 8 because I said it's oxygen, so that means it has to be 1, hydrogen. You have 4 plus 14, that's 18 total nucleons on the left. That means here you have 17, you need to have 1 on the right. Well, that's 1 proton, that's just a single proton, which is a hydrogen nucleus. Now this nuclear reaction is actually the first man-made nuclear reaction ever performed. People had found alpha particles decaying, or radioactive elements decaying into alpha particles, undergoing nuclear reactions, but it never really induced a nuclear reaction, man-made. This was done by our friend Ernest Rutherford. He did the experiments during World War I, published it in 1919. Let's talk a little more about it. He had a source of alpha particles, and he put it in a box containing air, and on one of the walls he had a zinc sulfide screen. Remember, zinc sulfide is if a particle hits it, it will give a flash of light, which you can see and detect the particle. And one thing about this screen, the zinc sulfide, is the flash of light looks a little different if it's an alpha particle that hits the zinc sulfide than if it's a hydrogen proton that hits the zinc sulfide. So what Rutherford saw was these look like hydrogen where it's hitting the screen. So the question is, where's the hydrogen coming from? Alpha particles going into air, how does hydrogen get into the picture? So what I'm going to do to you is I'm going to read to you a little bit about this experiment from the making of the atomic bomb. I want you to pay particular attention to all the control experiments that Rutherford did in order to rule out any other possible source of the hydrogen, and so he could just infer that this is actually this nuclear reaction taking place. We've talked about the scientific method, the importance of a hypothesis, and this reaction was essentially his hypothesis. But we talked about how you need to experimentally verify it, but we haven't really talked about how important controls are in experiments. So here we go. This is the making of the atomic bomb, and we're going to read about Rutherford. Okay, these newfound scintillations appeared to the eye to be about equal in brightness to hydrogen scintillations. Rutherford notes cautiously near the beginning of the revolutionary part 4 of his paper. He went after them. If they were hydrogen atoms, they still might be contaminants. He eliminated that possibility first. He showed that they could not be due merely to the hydrogen in water vapor, H2O. Drying the air even more thoroughly made little difference in their number. Dust might harbor hydrogen atoms. Like dangerous germs, he filtered the air he let into the box through long plugs of absorbent cotton, but found little change. Since the increase in hydrogen atoms occurred in air but not in oxygen or carbon dioxide, so he had eliminated the air and replaced it with oxygen, and then eliminated that, replaced it with pure carbon dioxide. Okay, since the increase in hydrogen atoms occurred in air but not oxygen or carbon dioxide, Rutherford deduced that it must be due either to nitrogen or to one of the other gases present in atmospheric air. And since air is 78% nitrogen, that gas appeared to be the likeliest candidate. He tested it simply by comparing scintillations from air to scintillations from pure nitrogen. The test confirmed his hunch. With pure nitrogen, the number of long-range scintillations under similar conditions was greater than in air. Finally, Rutherford established that hydrogen atoms came in fact from the nitrogen and not for the radioactive source alone. And then he made his stunning announcement, couching it as always in measured understatement of British science. From the results so far obtained, it is difficult to avoid the conclusion that the long-range atoms arising from the collision of alpha particles with nitrogen are not nitrogen atoms, but probably atoms of hydrogen. If this be the case, we must conclude that the nitrogen atom is disintegrated. Newspapers soon published the discovery in plainer words. Sir Ernest Rutherford, headlines blared in 1919, had split the atom. Let's look at another example. We're going to take our alpha particles and we're going to bombard beryllium-9. And what we're going to get is carbon-12 plus something else. Stop the video, figure out what something else is. What something else is a neutron. You have 4 plus 2 protons on the left. That means you have 6 protons. Here you already have 6 in the carbon, so you have to have 0. 9 plus 4 is 13. Here you have 12, so you need 1. 0, 1. That's a single neutron. A single neutron is released by this experiment. This was in fact the way James Chadwick discovered the existence of the neutron. Working in 1932, that great year for nuclear physics in England, he worked in Rutherford's lab and was a colleague of Rutherford's. Let's look at his experiment in a little more detail. He had an alpha particle, which he fired at beryllium. Out came some radiation, which he didn't know what it was. And that he fired and hit paraffin, which is a type of wax, has a lot of hydrogen in it. Out came hydrogen nuclei. So in goes alpha particles, out come hydrogen nuclei, but there's some intermediate which they didn't know what it was. There was 2 hypotheses going around. In France, there was a couple of scientists who had the hypothesis that alpha particles hitting beryllium gave carbon-13 plus a gamma ray, electromagnetic radiation, a photon. Chadwick's hypothesis was alpha particles hitting beryllium-9 create carbon-12 plus a neutral particle, the neutron. So what's even better than having a hypothesis to test is having 2 hypotheses, and you have an either-or situation, and you design an experiment to test them. So what Chadwick did is he did 2 types of analysis. First of all, he did an experiment where he replaced the paraffin by a bunch of other materials and seeing how the number of hydrogen was affected. And he also did some theoretical analysis, analyzing, much like what Compton did, what would happen if you had a photon come in, collide, and kick out a hydrogen. You're going to conserve energy, conserve momentum. Does the energy and momentum work out correctly? What he found is it did not. And he found that the only explanation for his experiments and his theoretical analysis was that there was some new particle that was neutral, about the same size as a proton, which means there was a neutron. Let me read you a little bit about his experiment. Chadwick's experiment to discover the neutron. Okay. Where am I? Yep. The hypothesis Chadwick proposed adopting should come as no surprise. If we suppose that the radiation is not a gamma radiation, but consists of particles of mass very nearly equal to that of the proton, all the difficulties concerning with collisions disappear, both with regard to their frequency and to the energy transfer to different masses. In order to explain the great penetrating power of the radiation, we must further assume that the particle has no net charge. We may suppose it to be a neutron. One wonders how nuclear physics made any progress before 1932, because the very first thing we talked about when we started our chapter on nuclear physics is that the nucleus contains protons and neutrons. Yet they did a whole lot of work before they even knew neutrons existed. Amazing. Let's try another example. We're going to take a proton, fire it at lithium-7. What we're going to get out is an alpha particle plus something else. Stop the video, figure out what something else is. What that something else is yet another alpha particle. Basically, the proton came in, 1 proton, 3 protons in lithium, gives you 4. You have 1 each or 2 each in the 2 alpha particles. 7 plus 1 is 8. 4 plus 4 is 8. So really, the proton came in and split the lithium atom truly into two pieces. It split the atom. Now, this was done by Cockcroft and Walton, working in England, again in that famous year 1932. And they were also working with Ernest Rutherford. They worked in Rutherford's lab. Now, in all the past experiments that we've looked at, we had alpha particles coming in. Because you have a source of alpha particles, you can get some radium or radon or polonium from Marie Curie, and they spit out alpha particles, and you can use them as your source. But here they're using protons, and they had to have fast protons. Why? Because if you think about it, here comes a proton with positive charge heading in to do nuclear experiments on the nucleus with a lot of positive charge. Positive charges repel each other. So in order to get the proton to get in close, you had to fire at the very high energy. So it'd move in and basically climb up what's known as the Coulomb barrier or overcome Coulomb repulsion. So you needed high energy protons. The only way to get those high energy protons is Cockcroft and Walton had to invent an accelerator that would accelerate their protons to very high energies. And using this accelerator, they were able then to do this experiment with lithium. Now, these accelerators, people use all these protons accelerated to high energies all the time nowadays to do nuclear physics. I want to recall that when we talked about positron emission tomography in a hospital, we needed to have nuclei that would emit positrons. So they usually had a half-life of maybe a couple hours, maybe an hour to 2 hours. And you had to create those, and you couldn't buy them from a company because they decay away before they could get to you to do the experiment. So you had to produce them in the hospital. So hospitals, what they typically have is some sort of accelerator. Usually it's a cyclotron that accelerates protons up to a very high energy, slams them into another isotope, and you get out a radioactive isotope that can then produce positrons, and that's what you use in positron emission tomography. So this idea of accelerating protons has been used over and over, both in technological applications and also in basic science. Okay, we talked a bit about 1932. Let's just review why it's so important. We saw in a previous lecture that positron, the positive electron, was discovered in 1932. We saw today that the neutron was discovered in 1932. We saw previously that hydrogen 2, the deuteron, heavy hydrogen, exists, and that was discovered to exist in 1932. And finally, Cockcroft and Walton accelerated their protons and created this nuclear reaction, all 1932. So, one other thing happened about the same time. In very early 1933, Adolf Hitler became the Chancellor of Germany. Another example. Here you have an alpha particle. Not everybody had access to accelerators, so we're going to talk about an old-fashioned experiment with alpha particles. Fire an alpha particle at aluminum-27. What you get out is a neutron plus something else. Figure out what that something else is. What that something else is phosphorus 30. So 2 plus 13 gives you 15. 0, 15. 4 plus 27 is 31. There's 1, so it's 30. Phosphorus 30. Now, phosphorus 30 has 15 protons and 15 neutrons in it. A very light isotopes like to have the same number of protons and neutrons, but phosphorus is getting a bit heavy. It really needs some neutrons to hold the whole thing together. So phosphorus 30 is unstable, and it's unstable because it doesn't have enough neutrons. Now, elements that have not enough neutrons will decay by positron decay, where they emit a positron and turn into something else. So let's review this from a previous lecture. Phosphorus 30 decays by positron decay to what? Stop the video, figure it out. Well, in a positron decay, one of the protons is going to turn into a neutron. The charge is going to be given off as a positron. So you'd have element 14, silicon 30, is what's produced. And this process has a half-life of about 2.5 minutes. It's radioactive decay, half-life of about 2.5 minutes. This experiment was done by Frederick and Irene Joliot-Curie in France in 1934, and it represents the first artificially produced radioactive isotope. So the first, you could get radioactive isotopes from uranium and all its products in this decay scheme. So people knew about radioactivity, but they never produced a new radioactive isotope in the lab. Here they did. It's interesting because you can detect neutrons. So you fire the alpha particles in aluminum, you detect neutrons, and you can also detect positrons. So what you find if you now take the alpha source away, your neutrons will immediately stop. But your positron signal is going to continue for several minutes. So I want to read to you a little bit from The Making of the Atomic Bomb about Frederick and Irene Joliot-Curie's first production of artificially produced radioactive isotope. Okay, where am I? After neutron emission ceased, positron emission continued, not stopping abruptly, but decreasing only over a period of time, like the radiation from a naturally radioactive element. What was going on? Joliot had been observing the particles with a cloud chamber, catching their ionizing tracks in a supersaturated fog. Now he switched to a Geiger counter and called in Irene. As he explained to a colleague the next day, I irradiate this target with alpha rays from my source. You can hear the Geiger counter clacking. I remove the source. The crackling ought to stop, but in fact it continues. The strange activity declined to half its initial intensity in about 3 minutes. They would hardly yet have dared to think of that period as a half-life. It might merely mark the erratic performance of the Geiger counter. A young German physicist who specialized in Geiger counters, Wolfgang Gentner, was working at the institute that year. Joliot asked him to check the lab instruments. The couple went off to a social evening they could find no excuse to avoid. The following morning, writes the colleague to whom Joliot spoke that day, the Joliots found on their desk a little handwritten note from Gentner, telling them that the Geiger counter was in perfect working order. They were now nearly certain that they had discovered how to make matter radioactive by artificial means. Let's do another example. We're going to take a neutron. So now we're going to use the neutron as our bombarding particle and bombard fluorine-19. What you get is an alpha particle plus something else. Stop the video, figure out what that is. Well, what you get is nitrogen-16. Nitrogen-16 is produced in this experiment. Nitrogen-16 is not a stable isotope. Remember, the stable isotope of nitrogen is nitrogen-14. That's the most common type. Nitrogen-16 has too many neutrons to be stable. So it's going to undergo decay. Now, I'm going to make this a little bit harder on you this time. I'm not going to tell you what the mechanism is for nuclear decay. I want you to figure out nitrogen, which has too many nuclei, how would it decay and what would it decay into? Stop the video, figure it out, and then we'll come back. Well, when you have too many neutrons, what usually happens is a neutron turns into a proton. So it turns into element 8, oxygen. If a neutron turns into a proton, you lose the charge, you pick up charge. You can't just produce charge automatically, so what happens is you emit an electron. There's a negative charge produced, the electron, which gets emitted by the nucleus. This is beta decay. The traditional, regular old beta minus beta decay. So what this neutron underwent beta decay to oxygen-16, half-life of about 7 seconds. This experiment was done by Enrico Fermi in Italy in 1934. Now, Enrico Fermi, why did he use neutrons to bombard the fluorine? Well, he thought to himself, neutrons are neutral. So if I fire a neutron at a charged nucleus, there's not going to be any electrostatic repulsion. I don't have to speed these neutrons up to a real high energy in order to overcome that Coulomb barrier and get the neutron into the nucleus. All you can do is you just set it in really slowly. You can float it in and bang, it'll hit it and cause a nuclear reaction. So he was trying to bombard all different elements with the neutron and see if he can induce artificial radioactivity. So he was doing this in Italy. Recall that Italy was also a fascist country, just like Germany, led by Mussolini. It was an ally of Germany. I want you to read you a little bit about Enrico Fermi's experiments on neutron bombardment. In the beginning, Fermi worked alone. He intended eventually to irradiate most of the elements in the periodic table, and he started methodically with the lightest. His source, he calculated, supplied him with more than 100,000 neutrons per second. Small cylindrical containers filled with substances tested, he would explain in his first report, were subjected to the action of radiation from this source during intervals of time varying from several minutes to several hours. Fermi first irradiated water, testing hydrogen and oxygen at the same time, then lithium, beryllium, boron, and carbon without inducing them to radioactivity. Laura Fermi, that's Fermi's wife, says he wavered then, discouraged by the lack of results. But Fermi seldom talked shop at home, and doubt seems unlikely. He knew from the Joliet-Curie work with aluminum, a little farther along, reacted with alphas, and neutrons should prove even more effective. In any case, he succeeded on his next attempt with fluorine. Calcium fluoride, irradiated for a few minutes and rapidly brought into the vicinity of the counter, caused in the first few moments an increase of pulses. The effect decreases rapidly, reaching the half-life in about 10 seconds. So, Fermi is now firing neutrons at a lot of different elements. And neutrons become the go-to source for causing nuclear reactions. So now, that was done in 1934. Let's kind of bring ourselves up to date and where we're heading for our next lecture. First of all, in the world of politics, 1936, Hitler and Germany reoccupy the Rhineland. The Rhineland was a little area in Germany that was bordered France. And according to the Treaty of Versailles, which ended World War I, Germany was not allowed to have troops in the Rhineland. It was a demilitarized zone. In 1936, Hitler marched his troops into the Rhineland, and Germany and England and France did nothing to stop him. 1937, the next year, one of the heroes of our story here in this lecture and in this whole modern physics story is Ernest Rutherford. He died in 1937, which meant England lost its greatest nuclear physicist. So, what we are now going into the late 90s is we are on the verge of war in Europe, and we are on the verge of the next great contribution of nuclear physics, that is the discovery of fission.